Hello, this is a video to recap what we talked about in class, which was how to complete the square, whatever that means. Now, the way we set it up was I asked you in the beginning of class to find the x-intercepts for this function x squared minus 6x minus 11. And you discovered quickly that this was unfactorable, and if we cannot factor, we cannot use the zero product rule to find the x-intercepts. However, if I could convert this somehow into vertex form, I won't need to use the zero product rule to find the x-intercepts. I just let y equals 0 and use inverses. Inverse subtract 20, inverse square, inverse absolute value, and we get two solutions. So here we can see the zero product rule is a nice way to solve quadratic equations in standard form if those equations are factorable, expressions that is. If they're not factorable, we need vertex form in order to solve for x-intercepts. So that's the issue that we're dealing with. So what if we have unfactorable quadratics and we need to find x-intercepts for those quadratics? So how do we get from standard form into vertex form? That's our objective. So the key involves perfect squares. So the first thing we're going to do is go off a little on a little side quest and say, how can I find or create perfect squares? So the answer is, if we have x squared minus 18x, there should be some number right here that if I added that number, this would be a perfect square. Now, I'll just show you what I mean quick so you can see. Here we have negative 18, which if we were making one of our X boxes, as I call them, or magic diamonds, or whatever they are, we would have the middle term here, and the last term would be here, which I don't know what it is. But for perfect squares, I remember that both of these two numbers were the same. So here's what you do. You say, all right, negative 18 is a middle term, which means that middle term has to be broken up into two identical factors. Boom, boom. And then, oops, I went a little far ahead of myself. Two identical factors. When you multiply them together, you get 81. So what I'm going to do to this expression is add the number 81, and I will have officially completed the square. And what that means is, essentially, by adding 81, I make it so that this expression has two identical factors. Since those factors are identical, we can express it as x minus 9 to the second power, which is squared. So that's what we mean by perfect square. Follow that algorithm again with x squared plus 22x. We recognize that 22 is the middle term, and if we bust that up into two of the same factor, we get 11 and 11, and we multiply that together, we get 121. So the missing puzzle piece is 121, and as soon as I add 121, this expression becomes factorable. Not just factorable, but the two factors will be identical. X plus 11 times x plus 11, or x plus 11 squared. Now what if the middle term is not even? I could still divide it into two equal parts by literally dividing it into two. Take 5 over 2, that's half of 5. So I have two of the same that are identical. When I multiply them together, 5 times 5 is 25, 2 times 2 is 4, that's 25 fourths. And we go back over here, x squared plus 5x plus 25 fourths. And then I can actually say this is factorable. What numbers multiply to give me 25 fourths that add up to 5? The answer is 5 halves and 5 halves. So my two factors are x plus 5 halves times x plus 5 halves, or x plus 5 halves squared. Continuing on here, this is 40. Take half of 40, you get 20. My magic number will be 400. Here at negative 2, I take half of negative 2, and then I multiply that together, and I get 1. Magic number is 1, which gives me, again, perfect squares. Probably the trickiest of all is when you have a fraction b value, but it's not hard to take half of a number. You literally take half by multiplying by half. In other words, when I have 9 halves times 1 half, I get 9 fourths. And if you multiply 9 fourths times 9 fourths, you get 81 sixteenths. Before I go any further on this, I'm going to point out that these middle numbers, that's when you take half of the b value, these middle numbers turn out to be part of my perfect square. Here's 11, 11, there's 11. Here's 5 halves, there's 5 halves. So it's nice to have these X boxes here because they're going to help you not only figure out what number has to be added, but also what the ultimate factors are going to look like. Now, to do completing the square as an algorithm, we do need to remember one last extra thing. The first thing is, if I see an expression like x squared minus 8x minus 3, the minus 3 is preventing perfection, so I kick it out. Then I look at the negative 8x, and I go over here, and I satisfy half of negative 8, which is negative 4, squared, which is 16. So I came up with the number 16, and I wanted to add that so that the first three terms form a quadratic, or a perfect square quadratic. But I cannot just add 16 without countering that by taking away 16. So I add 16 and group it with the first three. I take away 16 and group it with the last, or the leftovers. These first three terms factor to become x minus 4 times x minus 4, and negative 13 minus, or negative 3 minus 16 is negative 19. So this is switched now from standard form into vertex form. So here are two more examples. I would encourage you to pause the screen, because rather than me reading them to you, just pause the video and see how I've consistently used the same exact algorithm. Again, start with the kicking out the 24, take the middle term, cut it in half, square it, and that's the magic number, which must be countered by taking away that same number. This will be a perfect square, and then 24 subtract 49, negative 25. Same thing here. Pause the screen, check it out. Just to make sure that you're doing this right, you should understand that this equation in standard form is the same as this equation in vertex form. So you should be able to put them both into any graphing utility and only see one graph, because they're two different ways of saying the same truth. So make sure that you are checking your work here. So some quick examples, just going to go real quick. We've got these, and again, I said before that I'll just not talk you through it. I'm just going to put these up here because I think we're beating a dead horse. But maybe at least to say, yeah, okay, I'll do it here. Finding the magic number in this case, we've got the 7, and some people are going to say half of that is 3.5, and then they try to square it. Make 7 halves, half of 7. Then you could square it and get 49/4. It's way easier to do your work that way. So by adding 49/4 and then taking away 49/4, I create a perfect square up front, and I know that 7 halves will be the factor piece. Boom. And then this, I did some mental math. I was able to do this in my head. Either way, you should eventually get 15 1/4. And the same thing here. This is the other part I wanted to mention. 3 halves, if you have to take half of that, just take 3 halves times a half, which becomes 3/4. In other words, if you just double the denominator, you now have half of what you used to have. You square that and you're good to go. The magic number is 9/16. So we kick out the 1, we add 9/16 in its place, and the rest is history. All that can be checked by putting in both your answer and the given form and making sure that you only get one graph. I just wanted to look at this one. This is the worst case scenario is when you have a fraction that's not even numbered, but you could still do this exactly the same way as everything else. So don't be intimidated by fractions. They follow the same rules and procedures. Good. So for this particular assignment, I would like you to basically write all of these quadratic functions in vertex form by completing the square, just like I did in this video. So please do that, and we'll talk more about that later. Thanks.